it's a relation that interchanges the input and output values. And I'm going to put in parentheses here, or in quotations, x and y. You're changing your x and y values, basically. That's what an inverse relation is. So the way we'd represent that on a table, for example, like we have this original relation here. It says x is 0, 1, 2, 3, and 4, and y is 6, 4, 2, 0, -2. The inverse relation to that would simply be switch the x and y values. So the x value was 0 and the y value was 6. Now the x value is 6 and the y value is 0. We're just switching the x and y values. The x value was 1 and the y was 4. Now the x is 1 and now the x is 4 and the y is 1. Okay. So that's the idea. The idea for an inverse relation. Switch x and y values. That's what it would look like on a table. I love doing an inverse relation on a table. Super easy. I'm just going to write down the entire x column on the y column instead, or the x row, make it the y row, and vice versa. And then if I wanted to plot it, I would just plot my new points. So there's 6, 0, 4, 1, 2, 2, 0, 3, and -2, 4. And that's what the graph of the inverse relation would look like. So if I were doing the graph of the inverse relation, I would just plot those points. If I were doing the table, I switch the x and y values. That's the idea there. Okay. And now we'll take a look at an example. How do we do an example and find the inverse of it? Okay. Let's see. First thing here, it says find an equation for the inverse of the relation y equals 5x plus 8. So one thing to keep in mind is we want to say this could also be written in function notation. So sometimes it could be written as f of x equals 5x plus 8. Sometimes it's written as y equals 5x plus 8. It doesn't matter which way it's written. All right, just as long as you understand there that it could be written those two different ways. And then what we would do first to find an inverse, we're going to swap x and y. So even though this function started as y equals 5x plus 8, I'm going to say if written in function notation, we want to rewrite it as y equals 5x plus 8 just for our sake. And then when you swap x and y, you're just going to rewrite this as x equals 5y plus 8. And then the second part, we solve for y. We just have to get y by itself, and that's going to be how we find an inverse. So for this problem, for example, x equals 5y plus 8, we can go ahead and say subtract 8 from both sides. So x minus 8 equals 5y. And then divide both sides by 5. And we're going to get x minus 8 over 5 equals y. Okay, there's one issue with this problem that I don't like. We have y equals now. The one issue I have with this is it's not in slope-intercept form. So I want to rewrite it. Because right now it's y equals x minus 8 over 5. I can't tell what the slope is. I can't tell what the y-intercept is. So what I'd want to do is just literally write it as two different fractions. One of them is going to be, I could write as x over 5 minus 8 over 5. Or an even better way to write it is 1/5 times x minus 8/5. Now we're in slope-intercept form. And that's much easier to graph.
So I've got a question.
Yes.
I've seen this be the way you've done it, this whole unit. Is there a reason you don't like simplify 8/5 to like 1 3/5?
No, I mean, just in math, we generally want to leave things as improper fractions rather than mixed numbers. And the reason is for algebraic sake, if I had to add 1/5 and 8/5 for some reason, that's easier than saying 1/5 plus 1 3/5. So that's the only reason. It's just it's the mathematically appropriate way to leave a fraction. All right. So that's the only reason I leave it as 8/5. But when I'm graphing, if I wanted to change it to negative 1.6 for graphing purposes, that makes sense to me. Okay. All right. So that's how we would do these types of problems. Now, if I wanted to graph an inverse, I don't know why my graph's not here. I thought I had a graph on here. What I would do first is I would swap. That's weird. I had a graph on here. I don't know why it's not here. I would swap x and y values as well. So let's just go ahead and we're going to create our own table here. For some reason, our table's not here, so I'm not sure why. But I'm just going to create my own x and y points here. So this table, for some reason, should be on your paper, but it's not. So I'm just creating one right now. So this should have been given. I'm not sure why it's not on there. But what I want you guys to do now is create another table below and go ahead and fill in the inverse table. So fill in the inverse values. So there's the original and the inverse. So take a second to do that. All right, so you should have your graph inverse or your table inverse done, and then I had a grid for some reason that's not showing up now. Then we would just so I'm just gonna say right now, since we don't have a grid, we'll just say plot the points of both the original and the inverse. This is what we'd want to do on our graph, but for some reason I don't have a graph here. But I'll have you guys practice that on problem number 2 down here. Okay. Like I said, for some reason mine's not showing up, so I'm not sure why. That's weird. Okay. One thing to note is the graph of an inverse relation is a reflection of the graph of the original relation. And the line of reflection is y equals x. And I'll talk about that a little more when we do these 2 examples. But I want you guys to work on examples 1 and 2 right now. Examples 1 and 2. Try those 2 out. And
does that say reflection?
It does say reflection, yes. And we'll talk about that in a second here. Okay?
Okay.
And I'll talk about why that is, but I just need a graph to actually visually show you guys. So we'll take a look at that. Okay? So figure out problems 1 and 2, and then we'll talk about it. You'll end up with something that's like 1/2 x plus 1/2. Remember, we want to try and write it in that slope-intercept form at the end. So this is good. This is a correct answer. But this is better because this is something I can graph easily if needed. So we always want to be able to get it to graph easily if needed. Something else I didn't really talk about yet is we want to use this thing that looks like f to the negative 1 power almost. And this is inverse function notation. I didn't really mention this yet, and I should bring it up. So it doesn't really mean raised to the negative 1 power. That's not what it means. It's saying it's an inverse function. And we want to be able to write things like that because when we're dealing with x and y and we're dealing with 2 different equations, we want to distinguish the equations. So you can say, hey, the original equation, f of x, is 2x minus 1. Its inverse, f inverse of x, is 1/2 x plus 1/2. That's why 2 separate equations there. Okay, or that's why there's 2 different ways to write the f of x there. I had a little note up here too that says the symbol -1 in f inverse is not to be interpreted as an exponent. All right, so it's just, again, it's just a symbol that's showing, hey, this is what the inverse is. Okay? So just since I didn't mention that part yet. For problem 2, I already showed you guys how to do one of the points. We just want to take each point, figure out where they are. So this one, for example, was 2, 3 right here. So we'll replace that with 3, 2. And then the other was 2, 5, so we'll put a 5, 2. And then we had a 4, 3 that will make 3, 4. And then finally a 4, -2 that will make -2, 4. That's how we would put inverse points here for all of these values. All right, so if you were just given a series of points on a graph, that's how you'd find inverses for them. Okay, so it's possible that we could have inverses of nonlinear functions as well. So we've talked about the graph of x squared, the quadratic function. There's also x cubed. Those ones have inverses too. And what happens if we do the inverse of a nonlinear function, like x squared, for example, I would still plot the point 0, 0. Here's a point right here that looks like -1, 1 and 1, 1. So I'm going to put those points there. There's a point at -2, 4, so that's going to be 4, -2. There's a point at 2, 4, so I'm going to put a point at 4, 2. And this is what the inverse looks like. Okay, now that inverse right there is not a function. Okay, when I take the inverse of x squared, it's not a function. Why not? Why is it not a function?
Can't you not square a negative? Wait, no, that wouldn't do anything.
You're on the right track there. You're actually absolutely on the right track. It has something to do with squaring negatives. You can square a negative, because if I did -4 times -4 and I squared it, I'd get a positive 16. But think about, how do you tell if something's a function by looking at it on a graph? Okay, there it is. Nice work. It doesn't pass the vertical line test. Okay. That's exactly right. It doesn't pass the vertical line test. The vertical line test saying if I were to draw a vertical line, it should only hit the function at exactly 1 point. So like right there, for example, but it hits the function at 2 points. So that's why it doesn't pass the vertical line test. All right. Whereas the original relation, the red line, I draw a vertical line here, and it does pass the vertical line test. It only hits at 1 point there. Okay, but its inverse does not pass the vertical line test. That's the key there. That's how you can tell if an inverse is a function or not. Okay. So another way you could tell it is the original relation, or the original function, f of x equals x squared. All right. Does not pass what's called the horizontal line test. So just like there's a vertical line test to tell if something's a function, you could do what's called the horizontal line test to say, hey, is the inverse of this going to be a function? All right. So if we wanted to, we could do something called the horizontal line test to prove if an inverse is a function. So vertical line test proves, is this a function? Horizontal line test, is this inverse of this a function? Okay. So looking at this graph over here, this is y equals x cubed. This passes the vertical line test. Okay, it's a function. It's only hitting at 1 point there, 1 point there, for example. Does this pass the horizontal line test as well? Would its inverse also be a function? What do you guys think?
I think so.
Yeah, it totally does. So definitely passes the horizontal line test. We can draw points and it'll be fine. So let's see. And it's going to look something like this. So it passes the vertical line test when you draw the inverse. Okay, I sketch the inverse, it'll pass that vertical line test. Okay, so x cubed, the inverse, is also a function. That's good to know. Okay, now an example here. I just want us to try this one out. It says, find the inverse of f of x equals x squared. And for this function, we first started out as y equals x squared. And then we switch x and y, x equals y squared. And then to find the inverse of it, we are going to square root both sides. And when we square root both sides, what we have to do is we have to put a plus or minus in front of this radical on this side. When you undo a square, you put a plus or minus in front of the radical. So y equals plus or minus square root of x. And then we could technically write that as f inverse of x equals plus or minus square root of x. Now, if I were to graph this function, let me go ahead and switch screens here. When I find the inverse of this one, I switch x and y, x equals the square root of y, and then I square both sides, and I get x squared equals y. This time I don't do a plus or minus or anything, I just get y equals x squared, or f inverse of x equals x squared. Now, what happens though, if I go back to my Desmos screen and I try and graph this one, we're going to see something a little different. So when finding, an inverse, we also swap domain and range. So in this case, the domain and range happen to be the exact same thing. So for f inverse of x equals x squared, the domain is going to be 0 to infinity, and the range is going to be 0 to infinity. But that's what's going on there. Okay. Last one here says, find the inverse of f of x equals 2x cubed plus 1. So first we'll rewrite it as y equals 2x cubed plus 1. And then x equals 2y cubed plus 1. Subtract 1 from each side. X minus 1 equals 2y cubed. And then we divide both sides by 2. And then finally we cube root both sides. So this one's not going to be a nice, pretty function for us, unfortunately. But we're just going through the same algebraic steps. And we write this as a cubed root. And because it's a cubed root, we don't need to write a plus or minus in front of it, because you can have negative values come out of cube roots. So we don't need to worry about that plus or minus going in front. All right. But that's the idea for this, this last problem here. Okay. I've got a couple practice problems I want you guys to try. Problems 4 through 6. Identify the inverse of each of these functions. Okay. And problem number 4 there has this x is greater than or equal to 0, and that's just because it's a restricted domain problem. So you don't really need to worry about that too much. It's just saying that the reciprocal, or the inverse, is going to be just a positive root, not a positive and negative one. That's all that means. But try problems 3 through 6 now, writing inverses of each relation.